Welcome back to everybody.
Good morning, dear professor.
Morning. Then I will good morning as soon as I
Good morning.
good morning. So okay, CPI. I'm almost ready. Okay. So share. Hold on. Share window. Is there anybody asking to get in? Don't know. I share. There we go. So the idea in yesterday's lecture, it was to show that don't want this that we can use a quantum computer in order to try and break RSA. And as I said the day before, breaking RSA means not only figuring out the secret of somebody or breaking a very specific conversation we want to decode, but it might also break many protocols which are built upon RSA itself. So if we talking about modern cryptography, then we could say that the impact of quantum computers and Shor's algorithm on modern cryptographic infrastructure will be quite relevant. Another quantum algorithm, which I just mentioned, and just show you how it is. It's the quantum algorithm to break the discrete log problem. So, with quantum computing. The setup is similar to what we have for Shor's algorithm against RSA. Here, we do not want to compute the order of an element, but we want to compute to which order an element has to be raised in order to get what we have. And the idea is that even if, okay, here there are all of the computations, I won't bother you with them. The idea, I mean, if you are interested, we can go and see them in detail. But the idea is still to use the quantum Fourier transform and Hadamard gates, basically to test all of the elements of our group at the same time. And we expect to have a peak, that is to say, to have some outcome which is more probable than others for the value which correspond to the discrete. These are algorithms and problems which can be solved efficiently with a quantum computer. Well, let me recall that because that's something which has to be taken into consideration. By efficiently, I mean that we are able to have polynomial time algorithms, which are polynomial in the length of modulus n, in order to factor n. It doesn't mean that they don't take much time. As I told you yesterday, if we want to factorize 15, basically you can do that with pen and paper in less than a second. Whereas a quantum computer, at least the kind of quantum computers we have nowadays, it will require a few minutes. So do not think that quantum computer is faster than the computers you have on your desks. It's just that if a dimension of a problem grows, then the efficiency of a computer improves. So this is the idea of efficiency in this case. So given that most public key algorithms are based either on discrete log or factoring problem, what can we do? The idea of NIST and also of many people working in cryptography nowadays has been to, well, basically start right now thinking about some problems which might be hard even for quantum computers, and try and implement cryptographic methods or schemes based on these problems. Why thinking about them right now? Because the day we get a feasible quantum computer, it's too late. If we don't want to have to basically stop all e-commerce, e-voting, e-whatever, everything which is being done over the internet for a few months or perhaps some years, we have to be ready to have algorithms which are ready when and if quantum computers will become available. And so people have begun studying or rediscovering some techniques which were originally presented perhaps in the 70s of the last century, but which were left behind because they weren't as efficient as the systems based on discrete log or the factoring. So what we shall see today and tomorrow as well are algorithms which are, I will say, strictly worse than RSA and Argamar. They are not algorithms which are better. I mean, I've seen some people basically advertising a product saying on this device we use post-quantum cryptography, as if I were to say we use something which is much stronger than what you can buy from our competitors. That's false. That's marketing, but I hope they do not use post-quantum cryptography because if you want the same efficiency for a post-quantum algorithm as for RSA, then you are going to use a broken algorithm for post-quantum, for encryption. And you can break those algorithms just using a standard computer. For instance, and then I'll move to more details. For RSA, we deem nowadays a key of 468 bits is bits. Sorry, bits is deemed to be secure. For mechanisms like crypto systems, a key which is deemed to be secure is roughly of the order of 8 megabits. So there are a few order of magnitudes of difference. And the computational time, just to do the kind of operations you need in order to encrypt and decrypt, scales with the size of a key. So what you can do here in a few seconds, here might require quite some minutes to be executed. So if you want to make a list like crypto system, which is as efficient as RSA, you end up with a key which has the same size, but then to break that kind of crypto system is trivial with just your Core i5, Core i7 computers, no need for quantum computing. So, okay. This being said, let me do it. To add page. Yes. This being said, what kind of problems are reputed to be hard for a quantum computer? Hard, or at least not to be easier for a QC than for a classical computer. This is the kind of question we want. And in order to solve this question, or to address this question, basically we have to study classes of problems which are related to approximation. What people deem to be true is that these are approximation problems. And these kind of problems, we shall see, lead at least to three families of interrelated aspects or interrelated algorithms, which are the so-called learning with errors kind of problems. Then we have lattice-based cryptography. And then coding-based cryptography. In all of these cases, basically, what do we have? We do have a set of points or set of messages, let's say, things like that, which correspond to our secret key. And then what we transmit is a copy of one of these objects, which has been altered in a suitable way by introducing some noise or some deviation from what it was. To decode the system corresponds to recover from the altered version of a vector the original vector we sent. What we want is that this operation is easy for the intended recipient and hard for everybody else. And this leads basically to these kind of instances where we have to be very careful about how do we introduce noise in our message, and also on how we construct keys. I point out that, well, I mean, I don't know whether any of you is familiar with coding error correcting codes, but error correcting codes are something which is used basically in all communication systems. The idea of an error correcting code is that you send a message, M, and then your recipient receives M plus E, where E is a small e, is a vector with few non-zero components. And then the recipient applies some algorithm, let's call ECC, error correction, in order to recover from M plus E, M prime equals M, i.e. to find out what the error is. Error correcting codes work. There are many families of error correcting codes. Some are more efficient than others, but in any case, there is nothing secret about them. And also, basically, all systems, even embedded systems, things like an Arduino rather than, I mean, very low power devices, implement this sort of correction. So to move from M plus E, M, is suppose that all the hypotheses are satisfied, easy. However, if we want to construct a crypto system out of an error correcting code, we want that moving from M plus E to M has to be hard. And this sort of clashes with the original aim of codes. So what we have to do is to find some systems which are so large and so that you have so many parameters actually, then the code you have here, unless you have a backdoor or some way to cheat, it's too hard to implement. And this leads to having parameters which are way bigger than what you would expect for all kinds of public key cryptography. Now, a remark before I move to lattices, which is the topic I will start with, but it will not be the only topic we shall see today, is that, okay, this kind of operation, this kind of approximation for codes cryptography, we want a secret way to recover M from M plus E without knowing E, a secret way, a secret efficient way, and that in general the problem is not feasible. There is also another remark I would like to make before starting with post-quantum cryptography. But in general, PQ algorithms are not used to transmit data. You see, well, so what do we use them for? Sorry, see now that there is one message in the chat. Okay, it's fine. Good morning to you as well. To transmit data, but just to negotiate a key to be used with symmetric algorithm, e.g. AES. This is a remark which I think it's important because, I mean, the way we have seen RSA in the first lecture is a way in which we said Alice wants to send a message to Bob. So Alice has a message M, and then she computes C equals M to the E mod N, sends C to Bob. And then Bob computes C to the D mod N and recovers N. So this is the way we have seen RSA in our first lecture. But somehow this way to use RSA turns out not to be safe at all, because there are some informations you can extract from C if M is not a random element, there is something which has a semantic meaning. That is to say, if M is an encoding of some text, then it's not a random number. There is some structure on the way the bits of M are distributed, and part of this structure is reflected by C. At least the Lagrange symbol of M is the same as the Lagrange symbol of C. So there are some mathematical functions which are the same on M and on C. And that's something which should scare us quite a lot, because it tells us that the system is not semantically secure. That is to say, the system leaks some information of the messages. And actually, RSA, if implemented in this textbook way, leaks much more information than you might expect. Up to half of the bits of the message are leaked, unless some sort of padding is applied. One has to be careful about this. But nonetheless, the idea so is to use RSA to take M random, encode M as a ciphertext C, and then Bob uses C to the D mod N as a key for IS, the Advanced Encryption Standard. This is the way public key crypto systems are usually used. I point out also that using a symmetric system is always faster than using an asymmetric system. So this makes sense also because in this way, basically the communication has less overhead on the machines of the people which are communicating. Why am I saying this? Because, as a matter of fact, both LGMR and RSA in practice are used to transmit random numbers or random group elements. So when we think about post-quantum cryptography, we may say we do not care about what we are going to encrypt, but we want that once our protocol is over, both Alice and Bob have a shared secret which they may use in order to encode the rest of their communication. So the idea is that we use, let's say, we use public key cryptography to encode or to negotiate keys only properly, only to share the keys between Alice and Bob. And this leads to the idea that we do not need to be able to encode a message with our we just need to be able to share we just need both parties to get to the same secret. So the algorithm we shall consider are called KEP, where this abbreviation stands for Key Establishment Protocols. Before, so I hope that this is clear as an idea, because I mean, we are dispensing with all the parts of a crypto system which will require us to embed a message into the key space, and also to guarantee that there is semantic security. Because that sort of semantic security, that is to say, that what you are transmitting, that people cannot recognize from what you are transmitting, what you want to transmit, would complicate things a lot. So we shall see that, for instance, for lattice-based cryptography, but also for coding-based cryptography, we just pick one element at random, and that's what we are going to encode. And what Bob, let's say, we are playing the role of Alice, will have to do is to extract this random element. And then once he has done that, we can just communicate with each other without basically bothering about the meaning of the element which Bob has extracted as a key. It's just a bit string. So there is no need to embed any oral meaning in that string. Sorry. Another remark, IS is not broken by known quantum algorithm. This is a remark which I feel I have to do because it's not well, it's not obvious at all. It's not even straightforward to see to show this. But the idea is that even if you have a quantum computer, at least if at least according to the state of the art in 2023. So I'm not saying that there won't be any efficient algorithm against AES or quantum computers in the forthcoming years. At least for what we do know nowadays, a quantum computer is not sensibly faster than an ordinary computer in breaking AES. There is a small advantage in doing exhaustive search over the whole of the key space. So over the whole of 2 to 256 bits of a key space of AES if we use it according to the recommended parameters. But this is just a polynomial speedup, roughly a factor of 2 or 3 respect to classical computers. So basically, at least for the state of the art as of today, I keep on saying this because actually I have no idea whether in the close future there will be some kind of revolution in cryptography. Nowadays, that's what we have. We can use symmetric algorithms without being afraid of quantum computers. So if we have a key establishment protocol, we say, okay, stage 1, we share a key. Stage 2, we use AES, which is basically the standard. So what is the idea, or the basic idea, of both lattice-based and code-based crypto systems? Basically, you have a setting here, which in the lattice-based crypto system is a real vector space of dimension n, and in the case of code-based crypto systems is fq to the n, so it's a vector space of dimension n over fq. And then you have a discrete set of points, which is also an additive group contained here. But let's think about them as just discrete set of points. Here, those points are what I shall define it presently, but let's call it lattice. Lattice. By the way, there are two meanings in mathematics of the word lattice. I mean, there is lattice like this, which is related, for instance, to crystallographic lattices and things, and the action of groups on real vector spaces. And that is the meaning the word lattice will have today. And then there are lattices, which are algebraic structures where you have two operations. For instance, the lattice for subsets of a given set with intersection and union as operations. That's also called a lattice, but it's a completely different thing. So lattices for me will be these. Basically, they will be discrete set of points in a vector space or a real vector space of dimension n. Or in the case of a finite field, here we have embedded into fq to the n some vectors which belong to a vector space C, which is called of dimension k, C equals k, and C is called an nkq code. So the idea is also that all of these points have a certain distance between each other. In the real case, the distance will be the Euclidean distance. In the code-based case, the distance will be, well, is usually taken to be the Hamming distance. But in the code-based setting, I will say something about that tomorrow. You can also use different kinds of distances. I mean, there is a Hamming distance, but there are also people working with basically the Grassmann distance using subspace codes or things like that. So what's important is that we have a set which is sparse in our setting. And then what we encode is just, we want to transmit, let's say, this element here, this element here. So we just pick this element, then introduce a small error, a small change. So we end up with an element which is not on our lattice or not on our code anymore. And then we transmit the black dot we have. Okay. What the receiver must do, basically, he has the lattice. So basically, he gets this black dot here, and what the receiver, Bob in our case, must do is just to find a way to determine the closest point of the code or of the lattice to what he has received. So in this case, what can he do? He just starts from a point we have here, considers balls centered on this point, and as soon as he sees that there is one element of his spatial set, the code, the lattice, which is in that ball, he says, okay, so I shall correct my received vector with what we have here, close by. Well, from on the pictures I've drawn, I mean, they are not very good pictures, but they give idea, I hope. To determine the closest point of the lattice to the received point is easy. But we shall see there are some cases in which this might be made, even if the lattice is very simple. And that's the key of lattice-based cryptography. For coding theory, the converse is true. That is to say, the standard algorithm to correct an error, which is standard array decoding or syndrome decoding, which we shall see. I mean, we mention it tomorrow, but I mean, it's an algorithm which works for all error correcting codes. So it's the standard thing you find on all books on error correcting codes. Is an algorithm which is exponential in the size of the code. So that is the hard kind of algorithm. Then there are special families of codes for which this operation is easy. So in the coding-based approach, basically we have that the generic instance is hard. We have to find a way to make it easy for Bob to correct the error and then to output the message which was sent. With the lattice-based setting, the generic instance is somehow easy, but we have to find a way to make it hard for Eve, the interlooper, to recover the closest point to what has been set, because otherwise she could decode the message without throwing the key. So what I wanted to say is that both of these approaches are quite similar, almost the same in theory. I mean, the framework is the same, but then what we have to do in order to implement that is almost the opposite in one case. So now, what is a lattice? Well, the simplest definition we can give is that a lattice is a discrete additive subgroup of Rn. What is to say, it's just a set of points in Rn. So let's go L, AB. Sorry, why AB? It's a lattice. It's A1, AN, such that, let's say, this is a group. So if you sum two of these vectors, you still obtain a vector which is in the lattice. And for each pair of vectors which are in here, basically what you have is that they have at least a fixed distance inside. That is to say, in a lattice, the points are far away from each other. And you have a bound on how far away each point must be from all of the remaining points. And we can show is that basically we can take a basis for our lattice. Given a lattice, there is always at least a basis, just a set of vectors of Rn, so which I shall take to be linearly independent. I mean, here That is something which is a bit tricky, which I have to say. And then we just consider the span of these vectors, but instead of using, as for vector spaces, consider a span with real coefficients, we just consider the span of these vectors with integer coefficients. So let me make an example. Let's go into R2, which is the simplest example we can take. And then in R2, I take the points 1, 0, 0, 3. And my lattice, lambda, is the set of all elements alpha 3 beta, such that alpha beta is an integer. So, for instance, 0, 0 is in the lattice, 1, 0, 1, 3, etc. is in the lattice, but, I don't know, 0, 1 is not in our lattice. There are different ways also to define lattices. I mean, there are also more, let's say, mathematically elegant ways, perhaps, to define a lattice, but perhaps less evident in the sense that what we have in this case is that if you take R2 and quotient out the lattice itself, the points of the lattice, what you as thinking just as the additive group. So here you have the additive group of R2, and here we have this additive group here, which we have here. Then you end up with something which is compact. And one says, okay, a lattice can be defined as a discrete set whose quotient, which used quotient over Rn, gives you something which has finite measure. And it is compact, it always has finite measure. I mean, but those are more involved definitions for a lattice. We will not consider. Another thing which is nice to see is that if you quotient out this lattice of R2, you basically end up with a torus. What is called a flat torus? Because here there is 0, 0, let's say. Here there is 0, 3, okay. Here there is 1, 0. Here there is 1, 3. And then what you have is that basically you identify the points on these two sides of the rectangle, and you identify the points on these two sides. And so from a topological point of view, this object is the same as a torus. Because if you move here up, you get here, and then you end up down, below. And it's the same if you move to the right, you get here, and then you identify whatever is on the right-hand side of this arrow with what is here. And then you have a torus, a ringlet, if you wish, if you're not familiar with the word torus. So this is basically what we have. And a lattice is, well, it's not a vector space. It's a Z module, which is some structure which satisfies the same axioms of a vector space, but over the integers rather than over a field. So one cannot divide. And that's something which will turn out to be useful. Okay, a few small remark. Here I've taken these points as points with integers coefficients. That's fine. But in the definition of lattice, nothing requires us to use integral lattices. So we might have also a basis for a lattice, that is called a basis, which is made of rational numbers, and then consider the lattice spanned by these two vectors. There is nothing forbidding us from, I mean, we do not require the coefficients of all of the points of a lattice to be integers. This is fine, but if we instead of rational numbers, we end up using real numbers, then we have to be very careful because we might end up with a lattice by just considering the span of these numbers, or we may not. So for the purposes of this course, we shall just assume our lattices to be integral. That is to say, to have to be spanned by vectors which are defined over Z. Just a remark here, this is the remark, that even in R2, if we take the lattice, if we take the object spanned by this vector, alpha 1, where alpha is a real number given by this series, which is a series which converges, obviously, then we obtain a vector which does not span a lattice. Why? Because why? Because we just take all of the integral multiples of these vectors, so we would expect it to be basically the same thing as we had when we took, I don't know, pi 1 or something like that. But you see here that this is true, but it's also true that this limit, alpha times 10 to the 2 to the I, minus the integral part of this, goes to 0, just for the way we have built this object. So it's not true anymore in the thing spanned by this vector here, that 2 points are always at least at a fixed distance. So this is just to say everything works if we are careful, but we need to be careful in our assumptions. But once we take integral vectors, everything works. Now, we said a lattice resembles a vector space, so we shall consider now basically lattices which are integral, i.e. spanned by all vectors with entries Z, 1 and 2 full, i.e. such that their linear closure over the reals is all of Rn. So they are not contained in a subspace. And integral rational is the same as integral. And we see, and in this case, we see that these lattices always admit a basis. A basis formed by linearly independent, by n linearly independent vectors Rn. So a basis of a lattice in these cases is also a basis of a vector space. And this is something which will turn out to be very useful. Because if we are a vector space, we can have a change of basis. We can also think about equations for the change of basis. And how is it done in the case of lattices? Well, basically, let's say that B is a basis of a lattice. Then lambda can be written as B of x, where B is just a matrix represented by matrix. is B of x, where x is column vector in Zn, features, and we might ask, we may change the basis of lambda by means of an invertible matrix. This we can do. This we can always do as an idea. But the point is that we must send basis of a lattice into basis of a lattice. So we must send integral vectors into integral vectors. This is what we require, because a lattice, if it's spanned by vectors over the reals, for integral vectors, then all of its points will have coordinates which will be integers. And so if we change the basis, the lattice is the same, so the structure is still the same, we will have something which will be spawned once more by integers. But this means that basically we need a matrix in the general linear group, so the group of n times n square matrices with entries inside. We need something which is in this group here. And this is something which is has a very strong requirement. Because, I mean, if you think about a matrix, even if entries of this matrix are integers, when you compute its inverse, then you end up usually with a matrix whose entries are not integers anymore. For instance, if your matrix has determinant 2, and you compute its inverse, then somewhere you will have to divide by 2. I mean, and so you have a rational matrix, which is fine, but it's not an integral matrix anymore. How is it done? Remark, if M is in this group, since its inverse must also be in this group, then determinant of M must be an invertible element in Z. But the only two elements which you can admit an invertible, which can be inverted in Z, are plus or minus 1. So all of the elements of this group will have determinant plus 1 or minus 1. And this has an important consequence. The consequence is that we can define the determinant, which will be the volume of a lattice, as, let's say, that volume equals the determinant of B, where B is any matrix, B, modulus of that B, representing a basis. So that this we can do for lattices just because we are sure that as soon as we change a basis, the determinant of this the matrix we obtain changes by a factor of plus 1 or minus 1. We cannot do this for an arbitrary set of points or arbitrary basis in Rn. I mean, we can do that for basis in Rn if we want, but we cannot associate these to the geometric object we have, because as soon as we change basis in Rn, we change also this determinant. They are non-zero factor, whereas in a lattice, we are sure that nothing is going to change. Even here, a remark on the word volume. Think about two vectors like this in R2, but in R3 it's the same. And then you say that you see that this is, let's say, this is the vector AB, and this is the vector CD. Those are the coordinates of our points. And then you can see, using just the formulas from high school, that the area is exactly the determinant of ABCD, up to a factor. So, in a sense, the meaning of volume for that determinant is well posed, because this determinant corresponds to say that this is the kind of scenario. I mean, it corresponds to the intuitive idea we have of area rather than volume in a Euclidean space. Allora, remark two. Here I will just draw a lattice like this. And if we have a lattice like this, perhaps we can generate it by taking these two vectors as a basis for our lattice. And okay, that's fine. And so if we want to see what the volume of the lattice is, it is the area of this square. But as I said before, in the case of lattices, we can also take different kind of bases. For instance, we could take something like this as a basis. Should be correct. More or less. Plus one, yes, it should be basis of our lattice. Provided they are co-prime, because if we do the differences here, yeah, it should be okay. And what the remark I made before means is that the area of the dark blue square is the same as the area of the azure, of the light blue parallelogram. So in this sense, we can say, okay, the lattice is the same, just the basis has changed. The area is the same, but somehow there is something which is different between this representation here, this object here, and the object explored there. What is the difference? Well, okay, what is easier to use? Whatever you need to compute. If you need to compute properties in the lattice, well, the easiest thing to use is this basis here, the one given by the two vectors, the two orthogonal vectors here. You can also obtain, you will end up obtaining exactly the same results, exactly the same points, even if you use these order bases. And the computations will get messier. And that is the idea we shall use for cryptography. So the idea we shall use for cryptography is basically this. You have a lattice, you have a public base, and a private base. So this is what we have. To perform the private basis, tells you what the points of the lattice are. So if you want to pick a point at random of your lattice, you just pick up the private base, let's call it P. You compute P times X, where X is a vector containing all integers, and you end up with a point, let's call it lambda, belonging to our lattice. That's easy to do. Then you introduce noise. So you consider Px plus epsilon, where epsilon is a vector, and all this is also easy to do. But if the base is very skew, that is to say, it's like this, the azure one here, then to correct epsilon, this error turns out to be hard. Whereas if the basis is orthogonal, or almost orthogonal, as here, to correct, it's easy. So the public basis will be a basis where it's easy to find the points of a lattice, but that's the only thing which is going to be easy. The private base will be a base where it is easy to find the closest point of the lattice to a received vector. And now we'll see how this can be done. Okay, here there are a few references. Here there is the definition which we can give about compactness or having invariant measure, but I mean, don't care, at least for the time being. And then let me say just, okay, this is the problem I would like to present. But before getting there, here, okay, let's sum up what I've said before. So a basis, an independent vector CRNN generating the lattice. The dimension of this set is a priori is n, what we span. We always take m equals n. Two bases are related with transformations in GR and Z. And then we have that here it is. A lattice can be written as linear combinations with integers. What I want to say, okay, fundamental uniqueness here is that there is a notion, the notion here of volume, co-volume in this case. It's the determinant of the matrix we have there. And we can introduce right away a number which tells us how skew a lattice is. Because let's think about this. Here is what I wanted to say. That I want the. Let's have a lattice with basis v1, v2, v. We said covol, use the notation here, lambda equals determinant of. Okay, so this is what we have. But then suppose the basis vectors are all orthogonal to each other. Then the volume of a lattice is just, well, basically, if the vectors are all orthogonal, then our idea of volume is just to multiply the norms of these vectors among each other. So if we have something which is like this, it's a prism, so the volume of this stuff will be just the length of this vector times the length of this vector times the length of this vector, and so on. So in this case, it's just norm of V1 times norm of V. We want to estimate how skew our basis is. And this is basically the Hadamard factor, which is determinant of a basis over the scalar product of the norms of all of its vectors. And this number, it will be between 0, no, well, it will never be 0 because the determinant of B is non-zero, but it could be very, very small. Or if our lattice admits an orthogonal basis, it will be at most 1. And B is orthogonal, it will be at most 1. And basically what this tells us is how bad our basis is. When I say how bad our basis is, mind you, bad bases are not by themselves something we want to avoid. A bad basis is what we need in order to get public keys. A good basis is something we need in order to have efficient decoding. So we want basically this lattice to admit vectors which are almost orthogonal as a basis, and that is not guaranteed a priori. We have to impose that as a condition of an lattice construct. But also we want to be able to get a skew basis where implementing a correction is hard, and we are sure that implementing correction is hard because this number for those bases is going to be very, very low. This is the setup. Okay, and now let's move. I have to rearrange the pages, I see, because what I want to say is before to one problem, which is an important problem over in lattices, which is to find the smallest vector contained into this lattice. Let's say that we have points. Let me say here as well. But I will rearrange the pages before I give you these 5. Basically, here we have your lattices. Your lattice. Let's suppose that it's generated by these 2 vectors. So here +1. So this is how our lattice is done. Oh, sorry. It's hard to make mistakes involving things like this, but I can do it. Well, let's start with something like this. Okay. This is our lattice. So this is this. This is just to have a picture of what's going on. This is our lattice. And what you have to find is the shortest vector contained in this lattice. And if the lattice is, as I've drawn it here, basically you could guess that the shortest vector joining 2 points of the lattice will be either this one or this one, the one which has shortest norm among the 2 generators of the lattice I've given here. It will definitely not be this one. But okay, that's fine. So to solve the problem of the shortest vector in this lattice with this basis is easy. Now, let's suppose that the basis you are given is not what I've drawn there, but same lattice, it's something like this. No, we want a different color. Okay, done. Mm, mm, mm. So, mm, 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 mm. So it's a basis for the same lattice. But if I draw the lattice using these purple vectors, well, you don't know what is the shortest possible vector we can have. I mean, it's definitely none of the two vectors of the basis. That's sure. It might possibly be this vector here. Not purple. Different color. Well, we don't know. We have to confirm every time that we want to change the color. We do know, but it is not the. I mean, the orange vector I've drawn now is definitely shorter than both of the purple vectors here. I mean, we are using Euclidean distance, so what we see is what happens. But this orange vector is as long as the blue azure vector up there. And we know that the azure vector is not the shortest vector. So we have to do some sort of non-trivial computations or non-trivial analysis in order to figure out whether this is the shortest vector or not. Perhaps we can just write a few points of the lattice and then try and see, well, okay, I think that the shortest vector should be this rather than that. And then you do some sort of analysis of calculus or whatever, and you end up realizing that the shortest vector actually is neither of the purple nor the orange one, but it's a vector you can obtain as a non-trivial linear combination of the two purple vectors. So with coefficients which might also be large. I mean, here we are working dimension 2. For cryptography, you work in dimension 1000 or 2000 or something like that. So it's not that you have just an immediate algorithm to solve the problem. The idea, which dates basically back to Gauss, is that if you want the shortest vector of a lattice, you should look for the shortest vector in an, let's say, almost orthogonal basis. This is the idea to solve the SVP problem, shortest vector problem. That's what we are saying. Okay, it's not that there are no other ways to consider the SVP problem, but this is the best kind of algorithm we can implement. We take an orthogonal basis of our lattice on an almost orthogonal basis, like here, because in this case there is no orthogonal basis of the lattice we are considering. I mean, you see that there are no lines which are orthogonal here. So the basis cannot be orthogonal. And then you pick the shortest vector in there. And next, you use basically the triangle inequality, or a version of the triangle inequality, to persuade yourself and to prove that this is actually what we were looking for. So I see. So we are moving. We have almost got the kind of problem we want. So we are moving towards a problem where, for some people, it's easy to find the shortest vector. For some people, it's hard to find the shortest vector. That's a good place where to implement a crypto system. Well, if we are in dimension 2, then to find an almost orthogonal basis, it's easy. How? Basically, we use this algorithm, which is still due to Gauss, which is, if you look carefully at what it is, it's Gram-Schmidt with integer coefficients. So you have definitely seen Gram-Schmidt reduction in the first year linear algebra course in your undergraduate years. And the Gram-Schmidt reduction is something which requires basically plenty of computations. I mean, it's quite boring to perform, but it works. And given any basis for vectors, for real vector space, Gram-Schmidt ends up giving you an orthogonal basis for the same vector space. If you prefer, you can also get an orthonormal basis, because you can basically multiply and divide by all scalars Z. Here, what we do, we take our vectors, and then V1 and V2. If V2 is less than the norm of V2 is less than the norm of V1, we swap them. Otherwise, we compute the Fourier coefficient of V1 with respect to V2, and then we subtract from V2 the projection. Okay, V2, yeah, the projection of V2 on, sorry, V1, yeah, that's correct. We compute the Fourier coefficient, the integer part of, so V1 projected on V2, and then we remove from V2 this projection, and we iterate. As the algorithm goes on, this number gets smaller and smaller, and then it terminates as soon as n is 0. And then you get a basis which is as good as possible. Not only that, but here you also have that V2, that the basis is as orthogonal as possible. It's not orthogonal because here we have to take an integer vector, the integer part, which might be 0, but in any case, I mean, it's not required to be. So, in dimension 2, it's easy to perform Gaussian reduction. And this has also a nice application to an algorithm which you would not think to be a lattice-based algorithm, but it is that it actually is. An application of this algorithm here, which I want to show you because this shows that lattices appear also in unexpected places, is to compute the greatest common divisor of two numbers. So if you want to compute the greatest common divisor of two numbers, you can use the Euclidean algorithm. It works. It's efficient. You can also use Gram-Schmidt, Gaussian reduction. And I think it's worth mentioning because that's related to RSA. But RSA is not a lattice-based algorithm. So you see, well, okay, we have to be careful because if people have efficient algorithms for SVP problem or what, this orthonormalization problem, whatever, perhaps they can also find out efficient ways to factor the modulus of RSA. And actually, there is an algorithm of Cooper-Smith based upon lattice reduction. The idea is an extension of what I will show you in a few minutes. And that algorithm is an efficient algorithm to factor the modulus of RSA, provided you can find the shortest factorial lattice. So, but that is one of the most efficient ways to factor a composite number n, which is the product of two primes. So what is the idea? You have a and b, which are integers. You want GCD AB. And then you set up a lattice whose basis is 1, 0, A. Sorry, No, sorry. Now the converse. Okay, I mean, I couldn't make it work also like this, but A0 alpha, 0 B alpha, with alpha large. Let's say alpha larger than 10 to the fifth max, AB, something like that. So a very large lambda. And then you consider the lattice spanned by these two vectors. Okay, so these are all large and integer, of course. Otherwise, it would not be an integral lattice. And you say, what is the shortest vector in this lattice? Well, if you look at how I've set up these things, you see that the norm of a linear combination of these things, so let's say beta A0 alpha plus gamma 0 P alpha, is more or less no squared. So it's simple. It's beta A squared plus gamma B squared plus alpha squared beta, sorry, no, yeah, it's correct, beta plus gamma. But alpha squared is much larger than beta alpha squared and gamma beta B squared. So the norm of this vector is minimum. The norm has a minimum when beta plus gamma is as small as possible in modulus. But beta plus gamma, beta square plus gamma square, beta square plus gamma square. But this is as small as possible in modulus when basically beta plus gamma is as small as possible in modulus, i.e. when beta plus gamma is as small as possible. But what is the smallest linear combination in modulus of two integers? What is the smallest possible linear combination of two integers in modulus? The greatest common divisor. When beta plus gamma is the GCD. And so by solving the shortest vector problem, we have actually computed the greatest common divisor between A and B. And this is not a very efficient algorithm because alpha has to be large. I mean, we have to be sure that the term which dominates the norm is the term corresponding to alpha, because otherwise the algorithm will not work. But what's, at least to me, what was surprising is that you can formulate as a lattice-based algorithm also a problem which apparently is not lattice-based. And we shall see that for some crypto systems based on lattices, actually the crypto system is not based on a lattice. If you see the way it's formulated, the problem is given, say, well, no, where is my lattice? I mean, we are not taking integer points over the reals. We are not doing linear combinations over Z, at least not directly. But then you figure out that in order to break the crypto system, you have to find the shortest vector problem. And to have a crypto system being robust is equivalent to have the lattice given, which has a very skew basis, or where this kind of algorithm doesn't work. So that's the reason why those crypto systems we shall see are called lattice-based crypto systems. It's not that you at least for some of them. It's not that you just see the lattice there as a given datum. But the underlying mathematical structure, as for the ZCD problem, is the structure of a lattice. So let me just go on and observe that I mentioned the Gram-Schmidt as the b-dimensional analog or a variant of Gram-Schmidt for lattices of dimension 2. Nothing forbids you to do more or less the same if you are working with higher dimensions. And then the point is that then you have another algorithm, which is one of the most important algorithms in all of computer science, at least according to me, which is not, I'm not an authority on the topic, but I think that this is an important algorithm, at least to see at least one in your life, which is the LLL Nestler-Novas basis deduction algorithm. What is that? It's Gram-Schmidt, once more. It's Gram-Schmidt working over the integers and with a factor delta, which basically controls how good the result is going to turn out to be. So here, what we do, as you can see here from what's written here, basically at each step, we subtract from each vector its projection on the remaining vectors of a basis. But this is not the full projection, but just the projection where we take the integer which is closed to the Fourier coefficient of a vector over the other vectors. So we are just be a bit careful about this. Here we have a step in which basically we guarantee that the vectors are put in order of magnitude, and that's important for proving that this algorithm converges in polynomial time. So this is a polynomial time algorithm. The problem with this kind of algorithm is that basically it doesn't give you the best basis you can get, or a basis which is as orthogonal as possible. I mean, the parameter delta, you don't see it in here because this is written just to show that it is Gram-Schmidt, basically. But the parameter delta is basically used in order to estimate these coefficients, these Fourier coefficients. And it is a badness parameter. So the point is, if you want delta to be too small, perhaps the algorithm doesn't work because there is no basis which has that delta. If you take delta to be larger, then you get a very coarse result. So the basis is not orthogonal basis, but it's not even the most orthogonal basis you can get. So that's the badness of a badness parameter, and it's also what makes SVP an hard problem if a lattice is large. Because otherwise you could just say, well, I have a lattice, fine. I'll just put the lattice into the LLR basis, I take a basis, I use LLR reduction, and then I will get an orthogonal basis on an almost orthogonal basis for my lattice. Not quite. I will get an almost orthogonal basis within a factor of approximation. We want that for feasible factors of approximation, so for choices of delta, where the algorithm is going to end before the next century, basically, there are also better bases. So what we get is not the shortest vector in our lattice, but it's a short vector, which might work, might not work. In general, it will not work. And this is the reason why I had to mention LLL, because that's the solution here. Okay, here there is what I was saying before. Okay, the setup is different, but okay, it's fine. Okay, here the setup is slightly different, but it works. It's the same thing. I mean, it's equivalent to what I did before, because what I did before, I proved that to work. So I'm quite confident. Okay, but here as well, here we have these factors, gamma, which are the scale factors which we have to use in order to get a GCD. Here there is the oral remark, factoring with LLL. This is Coppersmith algorithm. It's quite more involved than the GCD algorithm. It doesn't work all of the time. Of course, if LLL were polynomial with perfect accuracy, this would work. But it's not polynomial with perfect accuracy. So this doesn't. Okay. So basically, right now, what we might want to do is to construct a crypto system or construct a key exchange protocol where we have a lattice lambda, lattice B basis, B almost, let's say, almost orthogonal basis. That is to say that B over norm of the rows of B, Bn. This is close to 1, as large as we want, close to 1. Then we take a matrix M belonging to GL and Z. We compute MB, but now we have a new basis for the same lattice, but with that B, well, the determinant, the modulus of the determinant of this matrix is the same as the modulus of the determinant of B. So we can just write B, but here we will have W1, Wn close to 0. Oh, there is a test of MR. Okay, so I think my phone will ring as well in a short while. Then. Okay, wish we can. Okay, but just say this, and then I will give just 5 minutes break. I don't know why. Okay, don't know. Okay, so this is close to 0. Then Alice picks a random point, random vector, let's say, vector x z to the n, compute. Okay, FB. Okay, and I don't think we are. Okay, yes, this is the test of the test message telling us that there might be problems. Okay, compute MB times x plus y random small vector in z to the n. And then let's just finish this. So this is what Alice is doing. And then sends S equals mbx plus y to Bob. Bob knows M, so Bob's computes m minus 1 S, which is bx plus m minus 1 y. And then and then nux for the closest point of the lattice to px plus and minus 1. And since basically this is an almost orthogonal base, to determine the closest point to the lattice, it's quite easy because all of the components of these vectors, of this vector, are as close as independent as possible. So this approximation problem is basically approximate each component of a vector with the closest integer allowed by lambda. So let's say the first component is 1, 2, is 1, 3, 7, whatever. In this case, what Bob does is if the first component is 6, he will assume that the correct value of the coefficient has to be 7. And then he updates the vector and see whether everything works. And if Alice has chosen y small enough, but that is one of the assumptions we have to have, then this works. Okay, now we will just do a 5 minutes pause or 10 minutes break, let's say, and then we shall resume at 12:15. Okay, so Ali. Okay, this is not the SVP. Let me see here. Okay. Window SM. Okay, so here there was as more as possible because we want those to. Sorry, here I'm noticing now that actually here I wrote beta alpha. Beta, no, it's correct. Beta plus gamma is correct. What I was writing here. When you improvise, that's what happens. So let's now move in the last academic hour of today to some algorithms which are based on lattices. In order to get there, I think that it's best first to see an algorithm which is based on lattices is slightly different from what we've seen before. Okay, here is the Gently-Galevi GCH, sorry, I'm not sure, algorithm, which is basically what I have mentioned to you before. Here we take a lattice, which we take a good basis for this lattice, and we want also that all the entries in this basis are comparatively small, that is between minus d and plus d. Then we take a scrambling matrix U in GL and Z, and we compute a new basis, which is this one. The rows of W are a bad basis for vector space, and the message will be a vector with small integer values, where delta is actually smaller, much smaller. And then what Lattice encodes is, okay, here the product is on the left-hand side rather than on the right-hand side. It's exactly the same as before. Representation encodes her message as a lattice point plus this error vector. And then what we have to do in order to decrypt, we just try to recover the closest vector to what we have received. Or in this case, what we do close to E, which is C, it's a C, it's not a E, it's C. And then we recover the message. There is a variant where instead of encoding in V, that is to say what has been done here, the message is here, and this is the error term, we just encode in the error, and the message is taken as random. In practice, as I was telling you before, these are key establishment protocols, so both of the vectors N and R are random. What interests Bob is to recover both of them, and then use the one which is used actually to negotiate the key. But if you know M, you know R, and vice versa. If you know. So that is an algorithm which is directly based upon lattices. There are also other kinds of algorithms where we use properties of lattices in order to basically construct something which is supposed to be secure. And true, well, and true means nth order truncated units or truncated polynomials. I mean, the people actually proposing and true say and true doesn't mean anything in particular, but okay. There are some backpronym for and true. Is a family of protocols where we work with polynomials, with integer coefficients, in order to provide efficient encoding. something which is supposed to be more efficient than the GGH algorithm. Because in order to have this algorithm to be secure, we need lattices which have huge dimensions. And here there is a reference. And then let's start with a toy example before moving to and through. This is actually a fully homomorphic encryption proposed by Gentry, Van Dyck, Gentry, Halevi, and I want to read his name. Okay. Vaitikuntanathan, which basically has the nice property that the product of two ciphertexts is an encryption of the product of two plaintexts, and the sum of two ciphertexts is the sum of the two plaintexts, is an encryption of the sum of the two plaintexts. This is useful because you could try to use this kind of encryption scheme in order to execute a program or a circuit on encrypted messages without having to decrypt the message itself. So that's the reason why it's studied. This leads to fully homomorphic encryption, which is a topic which is very, well, basically, it has been proposed in the 70s. Then in 2012, Gentry wrote his PhD thesis where he shows that it is actually possible to implement fully homomorphic encryption. And nowadays, there are many people studying problems in fully homomorphic encryption because it would allow you to compute on encrypted data without having to decrypt them. Think about a search engine which replies in a meaningful way without anybody knowing what you have been asking, which would be quite interesting from a privacy point of view. The problem with this system is that this protocol here encrypts just one bit. And we encrypt one bit with strings of 2 to the n, where n is large, bits to be used. So, okay, it's not efficient. It's not space efficient. It works. What is the idea? We just take two numbers, P and Q. Q is random, and P is, well, they might be primes, but it's not, I mean, it's better if they're primes, but it's not required for them to be primes. And then we have a message, which is just one single bit, 0 or 1. The encryption of the message is P times Q, so the product of these two numbers, which are odd, plus 2R, where R is a random number which is between P minus P over half and P over half P, plus our message. So our bit, which is 0 or 1, is masked by adding something which is PQ, which is general odd, plus 2R plus something else. And we say, well, what was the original bit? Was it 0 or was it 1? We do not know. Because in this case, okay, no, PQ is random, might be even. If we take Q to be prime, then we have a problem, because then the parity of C will be the same as the parity of N. P is just an integer in this range. So the encryption is this stuff. The decryption is C mod P mod 2. And let's see why. So C is PQ plus 2R plus. We do C mod P, and PQ mod P is 0. This is 2R plus M mod P. And we assume that if R is chosen in the range minus P over 2, as for R, P over 2, then 2r plus m is exactly the number, the integer number, 2r plus m is m. But now 2r plus m mod 2, this is equal to m mod 2, and this is equal to 1. So under the assumption, which is a non-trivial assumption, that this is true, and this is what forces R to be a special number, not just a random number, the system works. The public key, the key is, in this case, the number P, because P is what leads from this value here to this value here. This is not a public key crypto system. So you use the same key for encrypting and for decrypting. But the key is the number P. Q might be whatever. This is semantically secure. It's many things. The only problem this cryptography system has is that if you keep on using it and multiplying ciphertext among each other, then the noise term, that is to say this R term, might grow more than P over half. And if it might be better, and if it's larger than P over half, then the encryption doesn't work anymore. Because it's not true anymore that C mod P, which is 2R plus M mod P, is the same as 2R plus M. So this is what is called a somehow homomorphic crypto system. And then the brilliant idea, great idea of Gentry in his PhD thesis is that you can transform such a somehow homomorphic crypto system, which can perform just a limited number of AND operations, that is of products between ciphertexts, into a fully homomorphic crypto system where you can perform as many operations as you wish. Incidentally, homomorphic crypto systems are extremely slow. Much faster nowadays than they were a few years ago, but they are extremely slow. The other problem we have, we could consider, and which is related to where we will be going, is the problem of the approximate greatest common divisor. What is an approximate greatest common divisor? Well, greatest common divisor, we know that it is easy. But the point is that we want something where, say, we have P and Q. We want to determine values, something which is close to our terms, and which has a greatest common divisor which is as small as possible. In general, well, barring two. I mean, in general, or as large as possible, and conversely. And this is, in general, something which is not so simple or so easy to compute. Actually, it's one of the problems belonging to a family of learning with errors problems, where the only thing you can try to do is just all the possibilities and say, okay, this seems sort of right, so I'll keep that rather than not. So you have P and Q, then you slightly alter one of the two terms, and you say, well, I obtain a greatest common divisor, which is not what I expect. How was my term altered? I want to recover, it's still an approximation problem. I want to recover value R, which has been changed. And that's going to be tricky. So let's say a public key now crypto system based on these ideas. Let's start with P and Q, which are the primes. And then we generate the key by taking a Z, which is an element G, which is coprime with P, and we invert this element in ZP, which, well, okay, since this is different from 0, ZP is a field, so we are sure that we can invert it by using the Euclidean algorithm. Then we take an F, which is coprime with Q, and we invert this element in ZQ. And now we compute something which is, well, okay, which is something which, I mean, I am a geometer, I teach algebra and geometry. And when you teach geometry and algebra, linear algebra, there are some things you should never do. You should never mix up your moduli, because one thing are elements of ZP, reminder classes mod P. One thing are reminder classes mod Q. Integers are something else, entirely different. And mixing up integers with residual classes with different moduli is something which just destroys the algebraic structure you have. And this, if you are doing an algebraist, it's bad. If you are doing cryptography, it's exactly what you want to do. You want the structure of what's going on to be destroyed. And then what you do, you compute this number here, HQ, in ZQ, which is G, which was the number chosen at the very beginning, here in Z, with GCD between G and P equals to 1, divided in ZQ, which is a field, Q element, by PF. P is invertible because P is a prime different from Q. So we are quite sure we can do that. And F we have chosen in such a way as to have to be invertible. One is different from 0. And here once more, I stress, I know that perhaps I've been pedantic, but it's the key of the algorithm, that both F and G are integers. So public key, HQ, private key, F, which is here, and G to the minus 1. Encoding. We pick R, an integer, and we assume that to be smaller than P and Q. And then we compute the residue class mod Q of R times age in ZQ, age, Q, and Q as well. So this is something we can do. Then, once this has been done, Q, and both of them, we, okay, so here we have R times age in ZQ. We consider this class, we look at it as an element of Z, so we lift this class to Z, to the integers. We take the smallest integer contained, the smallest non-negative integer contained into this class. We get a number C dash, and we take the value of C dash modulus P. Don't do this if you're going to do an exam. Because, I mean, this class contains many numbers. C is just one of them. Why should we choose this rather than some other number? The reason why we should choose this is that our encoding will be C tilde, so this awful thing, plus a noise term, which is between minus P over 2 and P over 2. So this is the encoding we shall transmit. What does Bob do? Bob says, okay, first of all, let's work modulus Q. And modulus Q, let's multiply C by the class of PF modulus Q. C is RH modulus Q. So here we can write this, PF times RH modulus Q, plus, this is C tilde, PF epsilon modulus Q, which is the error term. But the first part is G times R modulus Q. The second part is P times FE modulus Q. Now we can lift this class regard this class, which is a congruence class modulus Q, as an integer. As an integer which is between minus Q minus 1 over 2 and plus Q minus 1 over 2. If we reduce all of these modulus P, because now we do with P, we have a second term which disappears. And so we end up with GR modulus P. Now we do know the inverse of G modulus P, so we can multiply by G minus 1 P, which is our secret key, and we ultimately get R. Or, well, the fact that all of this mess works, because this is quite a mess, and I agree with you if you think that this is quite messy, is that we have to be very, very careful on how we choose our numbers. We have to be careful that basically this lifting, this is where things might go amiss, from working modulus Q to working over the integers and then getting down and working modulus P is correct. And the result of these products in the integers are the same as the result of these products in the classes we are working with. And this is the reason why we have these assumptions on how epsilon must be, on how F must be, and also on how P and Q have to be chosen. However, if we have been careful, everything works. And this is an example of something which I would consider similar to N-true. We are using integers. But the point is that the ring of integers, perhaps we will see something of this in the coding theory course, speaking about polynomials and integers, has many properties which are similar to the ring of polynomials. In particular, if you have a ring of integers and you take some polynomial rings over fields, you have that both of them are Euclidean domains. In both of them, you can compute the GCDs of elements. In both of them are principal idea domains, so many of the algebraic properties are the same. But if you work with polynomials, you have more leeway. You can do more with a polynomial than what you can do with an integer. So instead of using huge integers, it might make sense to use polynomials with bounded degrees, which are not so too large. So in N-true, and this is an example of one version of N-true, which is called streamlined, there is an S, N-true prime. Basically, we do the same trick, but with polynomials. And here we have a ring R, whose elements are all classes of equivalence of polynomials with integer coefficients up to division by x to the p minus x minus 1, where x is a polynomial. Well, sorry, where p is a prime. Then we have the second ring, which is basically of polynomials with coefficients which are either +1 or -1 or 0, of the same degree as the polynomials you have in R. So these are trinary polynomials over R3. And then Q is an Oren prime, and then we have this third ring, because this is just a ring. I mean, this is not a reducible polynomial, so this is a ring of polynomials whose coefficients are basically between minus Q minus 1 over 2 and plus Q minus 1 over 2. So this is our setup. Before we had here Z instead of R, here we had ZP, and here there was ZQ. So the idea is, okay, here actually I require also that this is filled. Like I said, that we do not require X to P to be reducible here, but here it can be. So what do? We basically apply the same setup as before. We define a polynomial to be small if the coefficients are of in a Z3. We call it to be rounded if the coefficients are in these ranges. So even if we are in R, which let me recall, R is polynomials over the integers, not polynomials over ZP or something like that. We require this. And we define an operation round, which goes from the ring down here to R, which basically corresponds to choosing the smallest residue class, representative for residue class we were doing before. So I said, I take as a representative for this residue class the smallest non-negative element, which is in there. Round does the same. So it's a lifting, it's something which goes from R over Q to R. And this is something which, this is the kind of operation which, from the point of view of algebra, is at least debatable. And then, what do? We define an approximation, which is this. So here we have something which sends us polynomial to a trinary polynomial. And we want that projecting here into trinary polynomials a rounded thing. So we start from here, we round, and we start from here. We round, and we get here. And then we project and we go here, we reduce modulus 3. We obtain 0. This is the setup of include. Protocol. We take a polynomial in order over 3 which is invertible. We lift it to R, and we compute its inverse in R over 3. Exactly as we were doing before with in ZP. It's exactly the same setup. Then we take a random f tilde in R3, we lift it to R, and we project it to R over Q. And this is what we were doing before when we were going to work over ZQ. And then here, as you can see, as you will be able to see also as soon as it will give you this text, this kind of operation is exactly the same kind of operation which was giving us age before. The public key turns out to be this age. The private key is given by F and 1 over G. And code, as before, we take R tilde here, we lift it to an integer coefficient polynomial, we compute its projection times age in R over Q, and then we give as an output the rounding of this thing, which will be C0 plus epsilon. This is the same as introducing the noise term before. The decoding works in a similar way as before. So we work modulus Q here, then we lift what we have to over the integers, and then we project everything over the trinary polynomial. And this ultimately gives us the decryption of the text. To prove that the decryption works is not, as I was saying before, immediate, because, I mean, formally, what we do, as you can see here, is just some sort of elementary transformations. But there are some assumptions which are needed in order to be sure that we are not losing information with all of these modular reductions and the like. So we have to be careful on how P is chosen Q is chosen. You see that Q 2p must be at least 3 times this value, but then Q must be at least 16 times this value plus 1, and F and R will have at most W non-zero coefficients. So the algorithm is somehow fragile. If you do not follow these assumptions, then the encryption is not going to end up being to work. But under these assumptions, everything follows. And you have, here is the theorem basically showing that you are not going to end up with something unsavory. And then once you have done this, you have done what you needed. Now, before closing today's lecture, okay, here there is a version of n-true, located polynomial ring units. This is one of the interpretations of n-true, and it's correct. Here we have the general problem, but what characterizes n-true is this. N-true prime before as well as n-true. Recall that in the algorithm before, where was I? Here. Age is G over F, basically. That's what we have. In general and true, where there are less assumptions on the rings, we have that age is G over F modulus some polynomial of degree phi and zq. So the trick is you have age, which is a quotient somewhere, of two things which are supposed to be relatively small, and then we want to find G and F. How can we do that? The point is that we can do it by working over lattices. And we can do that by using something which is similar to the algorithm I shown before for computing the GCD of two numbers. Let's see how these two things are related. Okay, so let's move in terms. Okay, the point is to read what we were given before in terms of, as we're saying, determine the shortest vector in a lattice. What kind of lattice we are going to consider? Okay, let me just get, this is just n-true, and this is general n-true, but now we don't have time for seeing general n-true. I would rather go on how to solve n-true with lattices. Here we go. Remember, what we want to do, this is our assumption. In some setting of integers modulus q and given some polynomials, we want to find f and g such that f times age is g. And we set up this by looking for the shortest vector in a very specific kind of lattice. So f and g are unknown. Here we go. And here it is how we set up the lattice we have. Okay. The idea is f and g is small. Let's write it down. And let's now do the computations which we need. Okay. We have f of x times age of x is g of x. We know g of x. In lattice, mod Q. We want f of x, g of x. These are the unknown. So we take the lattice spanned by 1, age of x, and 0, comma q. And we claim that f of x, g of x is in this lattice. So it's a vector of a lattice, and it is small. So finding SVP gives f of x, g of x. Okay. So what is the equation we need to show? 1H, okay. So we set up this matrix here. Here we have identity matrix. Here we have a matrix of all the coefficients of age, and then we have cyclic permutation of all the coefficients of age, and here 0, and here we have q times the identity matrix. And now we observe that if here we have fx, gx, then we end up with what we want. Here, first row, my first column, here we have fx plus age x gx plus q gx equals 0. So what we have is, okay, fx, this implies that fx equals minus qe, minus hx gx mod q. From this condition here, this row first matrix product, and here we have okay, qgx. We have this holds, so we have this condition to hold, and then we have this theorem showing that everything is fine. That is to say that Fg is actually a shortest vector there. And how do we do? Okay, this is fine. F minus u by m equals G, if that holds. So how do we do? We basically have to do some estimate on the norms, on the volume of the lattice, and on the norms which are involved. And we see that basically in general, for lattices, we have that a vector, a short vector, or a lattice like envelope, is supposed by to have this length here. This length here, hold on, this length here, more or less. The norm of a vector we have there can be proved to be more or less of this order of magnitude. But what does this mean? It means that this vector is much shorter in the lattice than the vectors that we would expect. And so it's perhaps, if not the shortest vector, one of the shortest ones. And so using this vector, so using the SVP problem, we can get some good candidates for F and G. And then once you have good candidates, you just try and see what happens. Is more or less the same scenario as what we had at the beginning, where I said the GCD of these two numbers is a short vector in this lattice. And so you do estimates which are similar to the ones we did before. And this is what I wanted to say about these algorithms. So, okay, here I did, as usual, here I did my product the wrong way around. It doesn't change that much. Still should have written the other way. Okay, are there any questions? So just to conclude today's lecture, perhaps yes. So just to conclude this lecture, I say that like crypto systems work by destroying the algebraic structure of free rings of polynomials by using projections and liftings. And then we have incompatible with the operations in a can I say controlled setting. And here I stress that these operations are incompatible with these tools, these moves we do are tools which basically hide the algebraic structure. So from that point of view, they are bad from the point of view of a mathematician. But at the same time, we work in a controlled setting, as we did with the first algorithm we saw, the one of the integers, in order to be sure that decryption is possible, to ensure decryption is possible. What we have is that lattice-based algorithm can be used to recover the private key, secret key, from public key. How? Because given age, find GF such that GF equals age of the Q. And this is the reason why we study them as lattice-based algorithms. And in general, our security parameters will have to be such that this problem is hard. This must be hard. Okay, I think that for today, this is all I wanted to say. I've been told that, I mean, if you have any questions, please ask. I've been told that I have to send you a file to fill in for the doctorate, for it to be taken into account by tomorrow, I think, and I will do that. And so, I mean, if there are any questions or remarks or I'm here. Are there? If not, please. Any questions? If
No,
not,
Professor.
okay. Okay. So I'll hear from you tomorrow then. Okay.
See you tomorrow, Professor.
Tomorrow.